All right, good morning, everybody. Today we're going to continue talking about electrophilic aromatic substitution. We'll get into electrophilic aromatic halogenation, nitration, sulfonation, and Friedel-Crafts chemistry. We talked on these things briefly earlier, but we'll get into them in more mechanistic detail today. All right, so we talked last time that we can take a benzene ring and we can do this so-called electrophilic aromatic substitution reaction where we're going to replace the hydrogen with some sort of electrophile, right? And this works because we have aromatic systems in both the starting materials and the products. And we know that aromatic rings don't like to undergo addition chemistry because why? This is stable and this is less stable, right? I shouldn't say it's not stable, but it's less stable. And so you're losing that aromatic stabilization. The product's not aromatic, okay? And so in the process of the substitution, however, we preserve the aromaticity in the product, okay? We also talked about the fact that we can do all of these reactions, right? We can replace the hydrogen with a halogen if the halogen is chlorine or bromine. Pretty simple to do. You just use the halogen. You can bubble chlorine gas through the reaction mixture, or you can use liquid bromine, which is kind of most people's favorite way to do it. And you can end up forming new carbon-halogen bonds. This does not work for iodine, by the way. Okay? There are ways to put iodine on aromatic rings, but not through this particular set of conditions. The electrophile in this particular case is a chloronium or a bromonium ion, Br plus or Cl plus. However, they don't exist in solution. Okay, and we'll talk about that today when we talk about the mechanism. You really don't have chlorine plus floating around or bromine plus floating around in solution. We can do nitration. We can make carbon-nitrogen bonds through aromatic nitration, where we're using a mixture of nitric acid and sulfuric acid as the solvents. In this case, we're using the electrophile NO2 plus. We can replace the hydrogen with a sulfonic acid using sulfuric acid and SO3, also known as fuming sulfuric acid, which you can actually buy, which makes it nice and convenient. And this is useful because it allows us to make the soaps and detergents that you all use. Okay? This is an easy way of making certain surfactants, if you will, because these sulfonic acids typically are more soluble in water. Okay? The electrophile here is SO3H+, where the sulfur is positively charged. And then we can do the Friedel-Crafts alkylation and acylation. And what's really important about these particular reactions? We're making carbon-carbon bonds. That's right. So let's think real quick, what reactions do we know right now that can form a carbon-carbon bond? What's in your toolbox that can form a organometallic with what? Okay, so Grignards and lithium reagents, but how do they make carbon-carbon bonds? If I just throw them in with any carbon material? Okay, so we need some type of carbonyl, right? So we can take an alkyl halide, convert it to a Grignard, for example, react it with a carbonyl, make a carbon-carbon bond. That's one way that we know how to make carbon-carbon bonds. What's another way? Diels-Alder, and that's a very efficient way of making carbon-carbon bonds, as long as what we want to make are six-membered rings, right? So that works really well. So we've got Grignards, organometallics with carbonyls. We've got Diels-Alder. We've got Friedel-Crafts. What else do you know of? Last one might be harder for you to remember. But remember when we did cyanide? Cyanide will react with an alkyl halide, right? Through an SN2 reaction to make carbon-carbon bonds. Okay, so those are really the four reactions that you know right now to make carbon-carbon bonds really well. Oh, there's a fifth that you all should know. We talked about. Free radical, come on polymer people. Free radical polymerization, right? It allows you to make carbon-carbon bonds, a lot of them, right? So actually we've learned 5 ways to make carbon-carbon bonds, and the reality is there's only a few more general reactions that you can actually do to make carbon-carbon bonds. So it is really kind of the trick in organic chemistry is how do you make carbon-carbon bonds. So let's review real quick the general reaction mechanism with a general electrophile. So Dane comes in with benzene, and he wants to put an electrophile on it. How do we do that reaction? How do we draw the mechanism for that? Okay, so we got some electrophile, right? It could be chlorine plus, bromine plus, C plus, whatever. What's the first step?
So the double bond goes to electrophile.
Okay, so we have a pi bond reacting at the electrophilic site, right? How do I draw the rest of the double bonds in?
They're only, you sell the others for your other two, but you get
And where does the positive go?
on the bond and
Okay. Now, E plus can't exist by itself. There's always some kind of conjugate base around, right? So now what happens? You end up with the product, right? Pretty simple, straightforward reaction mechanism. The trick for all of you, right, is going to be how in the world do I get this stuff, right? Because this, that's easy, right? But this, how do we get the E plus? That's going to be a bit more tricky. And so we'll talk about that a little bit today as well, okay? This is what the reaction mechanism looks like. What does this resemble? It resembles an SN1 reaction mechanism energy profile. Does that make sense based on what we have here? Why does that make sense? We're forming a carbocation, although it is resonance stabilized because it's allylic, right? Okay. Why else does it resemble an SN1 reaction? It's two steps, right? The electrophile adds to the aromatic system, and then we eliminate to get back to the aromatic system. And so the energy reaction profile that we see for electrophilic aromatic substitution in SN1 look an awful lot alike, okay? You're going to have a carbocation intermediate, which is resonance delocalized. You got the second transition state, and you go to the product, right? So it looks very similar. So really, you don't have to even memorize an additional energy profile, right? This is really just like an SN1 type reaction, except it's not an SN1, right? What distinguishes it from an SN1? That's right, we don't have a leaving group, right? In an SN1, a chlorine or a protonated alcohol or whatever has to leave to give us a carbocation. Here, something is being added that gives us the carbocation, okay? So an electrophile in this first step. Now, does it make sense that this first step is the rate determining step? Why does it make sense? Well, it is the biggest peak, but why does it make sense that this is, what's going on here is the largest barrier? That's what I'm asking. Pardon? We're breaking a pi bond, but that's weak. But all bond breaking events are endothermic, right? So why is that so tall, though? This is also a bond breaking event. But that's right. We're going from a very stable system, an aromatic system, to a what? To a less stable, non-aromatic system, right? That's going to be high. So tell me in words why this is so small. Why is the second step such a small activation energy? Pardon? We're going back to an aromatic system, right? And so, yeah, this is going to have a very small energy of activation because this is already pretty high in energy, right? So really quickly we can form that aromatic system. Okay, very good. Halogenation. We can do, like I mentioned, chlorination and bromination very, very easily. Chlorination is less practical on a laboratory scale. Why? Well, I can buy both of these actually. But why would let's say Ian runs out of chlorobenzene and his boss says, make more chlorobenzene for me. Why would this be more problematic than the bromination? It's fairly reactive. It doesn't take too terribly long. What's the physical state of chlorine versus bromine? Gas versus liquid, right? Chemists we're not chemical engineers, right? And so we don't really get excited about having to run a bunch of pipes around, right? So dealing with chlorine gas is a lot more difficult than just simply going over to the bottle of bromine, putting it under the hood, and pouring it into a graduated cylinder and going, done, right? Yeah.
Is there a way to change substituents, like if you, like, the substituents out, instead of actually substitution with a double bond, actually like swap out the, like make the chlorine leave and then add a bromine?
There are ways to do that. Oh, we're not going to talk about that. But yes, different days kind of conversation. Okay. So pretty straightforward. You just have to have chlorine and iron trichloride. What is iron trichloride? It is a solid. That's a true statement. But what's its purpose there? What is it? What's it serving as? It's a catalyst. That's exactly right. The iron trichloride is a catalyst, okay? And so it lowers the activation energy. It's what gives us the chlorine plus, if you will, okay? Now, on my exams, sometimes I will just write chlorine and iron. And that does exactly the same thing. Why? How do you make iron trichloride? Chlorine and iron. That's right. So a lot of times chemists will simply take iron filings, because it's real cheap to go to Lowe's and buy a bucket of nails and cut them up, throw them into your reaction flask. I don't have to call Aldrich and have them send me a big bottle of iron trichloride. I can just use my bottle of chlorine, bubble it through with some iron filings, make my iron trichloride in situ, as we say, and since I'm bubbling it through in excess anyway, it doesn't really matter. Okay? We can do the same thing for the bromination. I can just use liquid bromine and iron as well. So those types of reagents will work just fine. But in either case, it's the iron trichloride or the iron tribromide that is actually the catalyst. So now, let's talk about the mechanism of how we get the electrophile. I'm not going to talk about the general electrophilic aromatic substitution reaction at this point. Let's just talk about how we get the electrophile. So let's look at chlorine. So I need chlorine plus. And I'm going to put it in air quotes here because it's not really there. So I've got iron trichloride plus chlorine gas, and I'm going to get Cl plus. How does that happen? What kind of reagent is iron trichloride? Is it a Lewis base or is it a Lewis acid? It is an acid. It is a Lewis acid, meaning that it wants to do what? It wants to accept an electron pair. Okay? So this is a Lewis acid. What about chlorine? It can be a Lewis base. And why can it be a Lewis base? We do have a lot of lone pairs. We ignore them, but in fact they're there, right? That's Cl2. What happens when I take a Lewis acid and a Lewis base and mix them together? Yeah. But that, I mean, it's not an untrue statement what you said, but it's not particularly relevant here. We get an adduct. The Lewis base reacts by donating a pair of electrons to the Lewis acid. And in doing that, we get Fe, and I'm just going to write it out like this. That's the adduct that we get. Where's the positive charge? Which chlorine? I've got 5 of them. The second from the right. Here? That is correct. Okay? I do the formal charge, and that's how I get chlorine plus. However, it's not that chlorine that actually does the chemistry. Because this is now positive and it's chlorine. Chlorine's pretty darn electronegative, right? Does it like to be positive? So what's it going to do? It's going to pull electrons towards itself. And the only way it can do that is from the things that it's bound to, right? And so it's going to pull electrons to itself. And that gives that chlorine a partial positive charge. So now what happens in the electrophilic aromatic substitution reaction, we get Cl plus 3. I push the electrons. Did you say boom?
No, no, not boom.
Oh. I was going to say, it doesn't go boom. Oops, not E at this time. Cl. We've just made the carbon-chlorine bond that we need to make. Now all we have to do is re-aromatize, regenerate our aromatic system. How do we do that? With a base. What base do we have here? Do we really have FeCl4 minus? We do, but we can think of it as Cl minus, because I know I have to get FeCl3 back because it's a catalyst, right? So this is really like FeCl3 plus Cl minus. And so then I get my product plus HCl plus FeCl3, which then goes back and recatalyzes the reaction. Same thing happens with bromine, except it's not chlorine, right? Pretty straightforward. The electrophilic aromatic halogenation reaction almost always appears, as I've been told, on the MCAT exam. Okay? In some form or fashion. For whatever reason, they like this mechanism. Okay? Now, this has had some very important uses. So, for example, Wellbutrin is made. It has an aromatic ring with a chlorine atom on it. You can't just go crude oil and get aromatic rings with halogens on them. You've got to do this synthetically. How do we do that? Chlorination. Okay? Wellbutrin is an antidepressant. It's pretty well used as an antidepressant. It's also used for some people who need to reduce nicotine cravings. It'll be prescribed for that. Got to have an aromatic ring with a halogen on it for that to happen. This molecule right here is an antihistamine. We're getting into that time of the year, right? Right? People are starting to have their allergy problems, right? So read on the back. You'll probably find that you have this particular molecule in your over-the-counter version or the generic version of whatever you're using, okay? And then these molecules, this is Agent Orange. Yeah. What was Agent Orange used for? Yeah, so if you're fighting in a jungle and you can't see your enemy, you'd like to be able to see your enemy, you've got a bunch of foliage in your way, eliminate the foliage. And that's what Agent Orange was for. The problem was Agent Orange causes all kinds of health problems. And soldiers were out in the jungles of Vietnam back in the 60s, and planes would fly by and dump their Agent Orange to defoliate the fighting field, and they got exposed to it. To this day, we're still spending billions of dollars on treating Vietnam-era veterans because of our choice to use these types of agents during warfare. They do. There's just all kinds of problems with Agent Orange. But it was an extremely good herbicide. It works really, really well for that. Even after Vietnam, people used it in their fields in America for some time before it was banned, actually. Okay? But it was a very effective, but it's a very simple molecule. This is an extremely simple molecule, right? It's just a mixture of these two compounds, and they do produce them from the aromatic ring and this electrophilic aromatic chlorination reaction that we've talked about, okay? Nitration and sulfonation is the same kind of general mechanism. We can take an aromatic ring, a mixture of nitric and sulfuric acid, and we can get nitrobenzene very, very easily. The nice thing about this is that you can take these nitrobenzenes and actually convert them into anilines through what kind of reaction? It is a reduction reaction. I'm replacing oxygens with hydrogen, so general reduction. What kind of reducing agent do you suppose might be useful here? Sodium borehydride is not strong enough. Lithium aluminum hydride technically would work. It's a bit overkill. My favorite is catalytic hydrogenation. You can actually use hydrogen gas and palladium and actually reduce the nitro group to the aniline. You can also use a mixture of iron and hydrochloric acid, or tin and hydrochloric acid, And we'll talk about those reactions later. But the cool thing is that there's really not an easy way of putting an amino group directly on a benzene. It can be done, but it's more difficult than to go through this two-step process where you do electrophilic aromatic nitration followed by reduction of the nitro group. And then sulfonation is just a mixture of sulfur trioxide sulfuric acid, what's also known as fuming sulfuric acid, and you can get the benzene sulfonic acids quite easily. Okay? The mechanisms here, I'm not going to draw these on the board just for time's sake. But what's kind of interesting about this mechanism? What's weird about it? Pardon? The middle step, where this is just losing the water?
When you think about those, do we focus or both those acids?
They are both acids, but are they both behaving as acids here? One of these acids is behaving as a base. If you look up the pKa values, you'll find that sulfuric acid is a stronger acid than nitric acid, even though they're both strong acids, which means that sulfuric acid functions as the acid and nitric acid functions as the base. And that blows people's minds. But remember, it's all relative, right? If I have a stronger acid than another acid, that one can function as a base, right? And so what happens when we mix nitric acid and sulfuric acid together, they're both clear, colorless liquids, you start to get this colored substance that's actually the nitronium ion. It's kind of yellowish color, okay? And so what happens is you protonate the OH of nitric acid, and you get what looks like water, right? This then simply leaves as water, and you get NO2+, which gives you this structure.
Which is almost radioactive, is so yellow.
No. It's not radioactive.
You have to use it like.
Oh. Yeah. So you all have done this, right? Yeah. And so you did a competition between two different things. And so this nitrogen is actually positively charged in solution, and it does function as the electrophile. So you can just substitute that into the reaction mechanism. Sulfur trioxide, this reaction mechanism is very, very easy. The SO3 just gets protonated, and you end up with a positively charged sulfur. There's your electrophile, and it reacts in the electrophilic aromatic substitution reaction using the general EAS mechanism that we've talked about. Okay? Any questions about that? So if I want to make chlorobenzene, what reagents do I need? Iron trichloride and chlorine gas. If I want to make nitrobenzene, I need nitric acid and sulfuric acid. If I want to make benzene sulfonic acid, I need sulfur trioxide and sulfuric acid. Very good. Now we can do the Friedel-Crafts acylation and alkylation reactions also. Now, on a practical level, Friedel-Crafts alkylation is less useful than Friedel-Crafts acylation. Can anybody kind of give me a hint as to why? If I sent Dane into the lab and I said, do a Friedel-Crafts alkylation, why would he tell me, Dr. Masterson, that's probably not going to be the best route to make that carbon-carbon bond? What might be? Okay. At some level, that's true. What's our electrophilic agent in the Friedel-Crafts alkylation? Carbocation. And what are they troublesome about? Rearrangements. So we got to be careful. Friedel-Crafts acylation, however, does not have a carbocation. It has an acylium ion, and we don't get rearrangements. Okay? And so anytime you're doing Friedel-Crafts alkylations, you have to at least be mindful of the fact that it can rearrange. So the Friedel-Crafts alkylations, we're going to use aluminum trichloride. What is that? A Lewis acid or a Lewis base? It is a Lewis acid. And it's going to promote the reaction, and then an alkyl halide. Almost always you use some type of alkyl chloride. You don't have to. You can use alkyl bromides as well. They work just fine. But alkyl chlorides are cheap, and they work quite well, and we form a new carbon-carbon bond. So for example, if we look at the reaction of benzene with ethyl chloride and aluminum trichloride, we get ethylbenzene. at least as the first reaction. We're going to talk later about the fact that the product is actually more reactive than the starting material, and so it continues to react and over-alkylate, which is a problem that you have to control. Okay? Is there any possibility of rearrangements here? No. How about for tert-butyl chloride? No. So we can make tert-butyl benzene this way as well. Any way that you have learned to make carbocations can technically be used in the Friedel-Crafts alkylation reaction. How have we learned to make carbocations? We have a whole bunch of carbocations, right? Pardon? Okay, so SN1, the first step. What reagents would we use? Oxymercuration never gives us a carbocation. But we could use an alkene plus sulfuric acid. Huh? It wouldn't do this chemistry. You got to have a carbocation. Yeah. At least I don't know of anybody that's done it that way. Alcohols and sulfuric acid give carbocations, right? Alkenes and sulfuric acid give carbocations. Everything that we've learned to make carbocations does this, okay? And now we've just learned a new way of making carbocations, okay? So how does that work? How would you draw the mechanism? How would you draw it, Amber? Yeah, you do. Let's say we've got isopropyl chloride and aluminum trichloride. How would we draw the mechanism? Aluminum trichloride is a Lewis acid, right? So it's got to react with what? The base on the left. What's the base on the left? Got those, right? Now what do I draw? What does this arrow tell me? Yep. And what's going to be my charges? So this was neutral. It just gained a pair of electrons. So what? Negative. And what about my chlorine? It is. You form that. Is that very stable? Nope. And so this leaves. We just converted that into a really good leaving group. And so now you've generated AlCl4 minus plus a carbocation. That carbocation is now the electrophile in the electrophilic aromatic substitution general reaction. Okay? And so we can do this chemistry pretty easily. We typically don't have undergraduates do this because aluminum trichloride down here in the south is actually kind of nasty to work with. It's not that it blows up or anything, but as soon as you open the bottle in moist air, it starts to billow out this white fume, which is hydrochloric acid. And you're sitting there going, and trying not to choke to death, okay? So kind of difficult for us to keep you alive, all right? So, but it is an easy reaction to do practically, okay? The Friedel-Crafts acylation is a little bit different. Right? We're starting off with acid chlorides. Does anybody remember how we make an acid chloride? It was on the test. I didn't ask you how to make acid chlorides in the test. I just asked you which reagent. Yep. And that was fair game. Does anybody remember how we made acid chlorides?
Looks like,
Why do we call it an acid chloride? What does it look like? What functional group does it look like? It looks like a carboxylic acid.
is the protonate, alcohol and oxalic acid have to leave and make chlorine?
Sort of. We actually take a carboxylic acid and react it with thionyl chloride. And you make acid chlorides very, very easily, okay? One of the easiest reactions in the world to do. You got a
He's
question?
like looking up and I can't see your face.
Oh, okay. Thought you were tipping your hat to me for some. All right. So, very, very similar to the Friedel-Crafts alkylation, except instead of making a carbon-carbon bond to an alkyl group, we're making it to a carbonyl, and so we can convert aromatic rings into ketones, right? So we can make ketones very, very easily. How else have we learned to make ketones? Oxidation of what? Secondary alcohols. If I take a secondary alcohol and what oxidizing agent? NABH4 is a reducing agent. PCC will work. What else will work? Jones reagent will work, and all those things that we call Jones in general will work, right? All those chromium reagents will work very well. But now we've got a way of making a ketone and at the same time making a carbon-carbon bond through the Friedel-Crafts acylation reaction. The trick is, how do we make the carbocation, quote unquote, that we need? It's actually an acylium ion. So let's think about that. So Sarah Polly comes in with an acid chloride. She mixes it with aluminum trichloride. Help me with the reaction mechanism, Sarah. Okay? Okay. That's not untrue, but there's a little more to the mechanism than that. The double bond going up to oxygen would put a positive charge here, and if that leaves that, it'd put a doubly positive charge there. Is that going to be likely? No. No. But I drew in these lone pairs for a reason. What can I do? What's that? This is an acylium ion, which is not what? It is not a carbocation. Therefore, no rearrangement. But wait a second. I'm forming a carbon-carbon bond, not a carbon-oxygen bond. Why is that? Why is my benzene not reacting at oxygen? It's the thing that's positively charged. Whoops. We have a resonance structure, right? That puts the positive charge on carbon. Is this a major or minor contributor? Minor contributor. But it's the reactive species. This is how it operates. And in reality, you just draw this. You got your benzene ring, and you just attack that carbon like that. That's the mechanism. Okay? But the carbon has a lot of positive character because of this minor contributor to the resonance structure. Now, wait a second. Why is this the minor contributor? Carbon is less electronegative than oxygen. Why is this the minor contributor and this is the major contributor? That's right. This does not have an octet for carbon. Every atom here has an octet, right? Very good. There are some facts that you need to know about Friedel-Crafts acylation and alkylation. Vinyl halides and aryl halides do not react in the Friedel-Crafts alkylation reaction. It has to be an sp3 hybridized carbon halogen bond. These are what kind of hybridization between the carbon and chlorine? sp2. If I take this vinyl halide or this aryl halide and I place it in with aluminum trichloride cannot remove the chlorine. Why not? Well, let's think about that. This does not happen. Why? doesn't mess with the aromaticity at all, because the chlorine is in this plane and the aromatic pi orbitals are up above and below that plane, right? So it's orthogonal. So it has nothing to do with aromaticity per se. It has everything to do with the fact that it's sp2 hybridized. Why? Why can I not generate that carbocation easily? A carbocation likes to be what geometry? No. Likes to be trigonal planar, right? We'd like to be trigonal planar with the p orbital above and below the plane. Can that happen there? No, it cannot. So remember that a carbocation is a p orbital, an unhybridized p orbital on an sp2 hybridized carbon, right? This is a carbocation on an sp2 hybridized carbon, but it's not. It can't be the shape of a p orbital. It would be an sp2 hybridized orbital with a positive charge in it, or the absence of electrons, I should say, right? Won't work, okay? So these types of alkyl, or these types of halides, I shouldn't call them alkyl because they're not, will not work in the Friedel-Crafts alkylation reaction. You have to have an sp3 hybridized carbon halogen bond. Okay?
Could you just reduce that bottom halide and then react?
Sure. Yeah, in theory we could. Yeah, in theory you could take this, reduce the pi bond, and then it would be very reactive. Yeah. That's easier said than done because the reducing conditions will also remove the halogen, usually. But it's, on paper, it's theoretically correct. Yeah. Don't forget about rearrangements. Gabriella comes in and wants to make a carbon-carbon bond between this red carbon and this aromatic ring. So she says, okay, we'll start off with this. We'll use aluminum trichloride. That'll give me the carbocation, which we'll then add. However, she goes and runs the NMR, and she finds out that that red carbon never got attached to the aromatic ring. Alkylation occurred, but so did a rearrangement. Why? That's right. That's right. So the cardinal rule. If we remove that chlorine, we get what kind of carbocation? Secondary. And now we can have a shift. What shifts? This hydride will shift over to that carbocation, and we end up with what kind of? Tertiary. That's right. Okay. Obry comes in, and he wants to make propylbenzene. And he says, well, I'll just start off with one propyl chloride, do this, and he finds out that instead he doesn't get N-propylbenzene, he gets isopropylbenzene. Because aluminum trichloride will start to remove this chlorine, and then you get a hydride shift to a secondary carbocation. You never actually generate a true primary carbocation. As the chlorine is coming off, the hydride shift's occurring at the same time, because primary carbocations are so unstable. But nonetheless, you'll get that rearrangement. Okay? So we've got to pay attention to rearrangements. Okay? Other functional groups can be used as starting materials. Anything that can form a carbocation is technically fair game. So if we take an alkene, sulfuric acid, we get a carbocation. In this case, it's a secondary carbocation. So Obry could take benzene and this cyclohexene, add sulfuric acid to it, and what would his product be? That's right. You would have benzene plus this, sulfuric acid, he would get that.
What would that be called?
I'd call it phenylcyclohexane. That's how I would name it. Or you could name it cyclohexyl benzene. Two ways to name it. Alcohols also work. Here we're taking tert-butanol, sulfuric acid. You get a tertiary carbocation. It can be used. Before we settled on the reaction you all did this week in lab, we used to actually do this bottom reaction where we would take We didn't use benzene. We used, I think, toluene or something, and tert-butanol, sulfuric acid, and the students did electrophilic aromatic substitution, making that carbon-carbon bond. So anything that can generate carbocations can be used in the Friedel-Crafts chemistry, right? We have to worry about rearrangements, and we have to remember that there are certain alkyl halides, or certain halides, I should say, that won't work. Okay? So anything that can generate a carbocation can technically do this reaction. So keep that in mind. Okay? Let's look at some important reactions. So here we have an aromatic ring. We have an acid chloride. We have a tertiary amine, which actually is fairly unreactive in these situations. You take aluminum trichloride. We now form a carbon-carbon bond here. And in doing so, what kind of ring did we just form? A six-membered ring. Very similar to a Diels-Alder. But why would we not do a Diels-Alder here? It's very difficult to see how we would get a diene and a dienophile that would give us this ring structure. Okay? So you start off with this bicyclic structure. We now have a tricyclic structure, which we need here. Do a few steps, and you have LSD. Okay? A few minor steps that we won't talk about, and you get LSD. Huh? Not right off the top of my head. No, I'd have to think about it. We could figure it out, though, but we're not going to. So you could make LSD. Now, LSD actually has legitimate uses. I mean, it's been used in veterinary medicine for quite some time, and among other non-legitimate uses.